Good evening, everyone. Welcome to the Carolina Weather Group. We're happy to have you this evening. And let me tell you, this show is for the weather geeks out there. You know, we do a big variety of shows, from talking about storms to things that are going on in social science. Well, tonight we're going to be diving deep into modeling. And I know Jared is just ecstatic about this. He cannot wait. So we're going to be talking about that tonight. NOAA just introduced some new supercomputers that are going to help forecasting and climate forecasting get better and better. And we all know the better data that we have, the better our forecast can be. So we're happy to have Mr. Brian Gross on with us tonight, as well as David Michaud. And we are looking forward to diving into this. So, you know, normally I lead the conversations, but since this is like in Jared's playground, I'm going to just toss it over to you, Jared, and I'll let you get us started.
Yeah, no, that sounds good. Gentlemen, welcome to the program. So, I mean, let's just get into it. I think the best way that we can start this is talking about just how much modeling NCEP runs, how many models you produce a day, and how much computing power you generally need for that sort of thing.
So right now, we run between 20 and 30 applications every day, and sometimes multiple times a day, right? And how much computing power do they take? Well, they span all the way from the global models, right? The US runs global models, the Europeans run global models, all the way down to pretty small scale models that focus on individual hurricanes, right? And we size those models to use as much computing as is available to us. It's pretty rare that we have idle computing cores sitting there.
Yeah. So in terms of the actual computing capacity, that requires, so this recent upgrade that we had, we increased our computing capacity by almost 3 times. So when you look at just kind of putting it in layman terms of, what we have for computing capacity, we have 2 supercomputers that run in a primary and a backup capacity, and we can talk more about the configuration and get into the details of that. But just at a super high level, one of those supercomputers which runs these models, it can calculate about 12 quadrillion calculations per second. So that's 12 with 15 zeros. Per second. So just kind of putting that into terms that you might get your head wrapped around, how many calculations that is. If you were to take every person on Earth and provide them a handheld calculator, everyone, and you ask them to do a simple math equation and just do that over and over and over and over and over as quick as you can, it would take every person on Earth about 1 month to do what our system, one of our systems can do in 1 second. So just to kind of give you an idea of the type of computing capacity that this requires.
How does that compare to a typical home computer in terms of?
Yeah, that's a great question. So at home you might have a laptop or a system that might have a quad core processor, so like maybe 4 cores there. If you look at one of our systems, we have, just from in terms of size, one of those systems would have 10 cabinets. So think of a cabinet as like a refrigerator sized piece of equipment. And in each of those pieces of, in each of those racks, we have, subcomponents. So we have about 256 nodes in each of those. And then within each of those nodes, we have 2 processors, and each of those processors has 64 cores of capability. So when you kind of total all that together, you have a system at home that's a quad core. One of our systems has about 327,640 cores on it. So that's just kind of from a comparison perspective, it's pretty impressive.
So that's like a small city full of laptops all humming away at our problems.
Right. And then you look at the power consumption of that, you couldn't run one of those in your home. So, one of those supercomputers would take about just about a megawatt of power to run. So if you were to plug that in at home and run it full time, like we do, your utility bill would be probably somewhere around $1 to $1.5 million a year.
I'm assuming you guys are getting some kind of break on the power there at the center.
So that's one of the considerations, right? So when you look at where to locate these, you got to look at your power delivery cost and so on, and what the climate there looks like, and that kind of coupled with the type of network connection that you can get. So much like the connectivity varies going to the home, connectivity varies going to various cities and data centers. So you have to take that into account. You have to take in your delivered power cost into account, and so it gets pretty hefty quick. I looked online tonight, just out of curiosity. So if you were to, we rank about 49 and 50th in the world in terms of the fastest computers, our primary and backup. The fastest computer in the world's running at peak theoretical speed of around 1.6 exaflops, which is, I think, like 1.6 quintillion calculations per second. So that would run you about, somewhere around 23 megawatts to run. So that would cost you somewhere in the $20 to $30 million range to plug in at home and run.
You also have to keep in mind that for every megawatt of power that the computer consumes, you're going to, I guess, use that much more electricity to keep it cool, right? Yeah,
absolutely. So it takes quite a bit of cooling as well to run through. So the system that we just put in place is a liquid cooled system. So in order to run that, you'd have to have the right type of cooling system, and then you'd run some fairly hefty plumbing, and then that plumbing actually routes through the cabinet and over the processor to keep everything cool on a full-time basis to kind of dissipate all that sort of heat. So it gets, like I say, it gets pretty complex quick when you think of the logistics of what it takes to run one of these.
People knowing from like the Weather Channel and from Weather Twitter and all that, it's always, the Europeans versus the United States. ECMWF, they run their model, as we talked about, as we alluded to briefly. We run our suite of models here in the US, from the GFS Global all the way down to the HWRF. How does the new upgrade in like computing power terms, how does that put us next to the ECMWF, and what would that enable us to do?
It's important to understand that if you look at any country in the world, right, which country has the most different kinds of weather, I'll say, it's us, right? We have winter weather, we have summer thunderstorms, some of them severe, flash flooding, hurricanes, cold air outbreaks, and heat waves. We have the impacts of two coasts that we need to deal with. So the spectrum of weather phenomena that we need to model, I think, is greater than any other country in the world. And this is why we have to run all of these multiple modeling systems to try and attack those prediction problems. So there is a direct relationship to the things that we can do with our models and the computing power that we have. There's usually 4 areas that we look at to improve our models and when we get additional computing. Probably the easiest to understand is model resolution. So we can increase the resolution of our global models and our limited area systems, the ones that focus on the US. We can improve how comprehensive the models are. We can add additional physical phenomena to our models, the way the rain falls, the way snow melts into rain up in the sky, the formation of thunderheads, anvils and that sort of thing. We can run additional simulations to help us quantify our certainty in any particular numerical forecast, right? If you run 10 different forecasts with slightly different initial conditions, and you get pretty close to the same answer out of all 10 of those, you're pretty confident in that forecast. If you get 10 completely different answers, it becomes much tougher to be confident in any one of those forecasts. And then the last area is how well and how many observations we can assimilate, right? The forecast always starts with the ingestion of data to formulate an initial condition for the forecast, and gathering all of that information, ingesting them, assimilating them into the modeling system. That takes an awful lot of computing power. So resolution, model comprehensiveness, ensemble size, and data assimilation. Those are the four big areas that we use the computing power for. And every one of these, you can see an improvement in our own scores, right? Now, the Europeans are doing the same thing too, right? As we get better, they get better too. So I don't know if catching the Europeans is so much of an issue. We want to keep improving so that we can deliver the best possible numerical guidance to the forecasters as possible for all of the weather phenomena across the country.
Diving in a little bit more, with the models, I know the last big upgrade to the GFS, and really something that it seems like you're trying to consolidate all the models around, is the FE3 Core. Talk to us a little bit about that, what that's been like, and if and what might be coming now that we have this new capability.
We adopted the FE3 dynamical core for the global system first, and now what we're doing, remember we talked about those 20 to 30 applications. We're really trying to consolidate many of those. For example, we have upwards of 5 or 10 mesoscale models running. We're going to try and consolidate those into a single mesoscale system. And we're trying to base that mesoscale system on the FE3 die core as well. So we'll have global models, limited area models, even the hurricane systems, the new hurricane analysis and forecast system that we're developing. All of those are based on the FE3 dynamical core. So we're trying to simplify the structure and components that we use in our modeling system so that we can upgrade them more efficiently. We can accelerate the pace of innovation that we bring into the models, and we can apply those innovations across the spectrum of applications.
I know that something interesting that that's happened in the last couple of years is that the model, as I recall, has been open sourced.
That is a great point. One of the other things that we're trying to do as we're trying to consolidate our modeling suite, and we're adding computing power, we're also trying to tap into the entire numerical weather prediction enterprise across the United States. And we're doing that by making the global modeling system, the mesoscale modeling system, which we call the rapid refresh forecast system, because we want to get that hourly cadence that the RAP-HER provides us today. We're trying to get all those codes into GitHub and make them publicly available. So anyone in theory could download, and if they have the computing to do it, they can run their own forecast and in fact, poke around in the code, try out some perhaps innovative ideas, with the ideas that those innovations are going to come back and we're going to be able to put them into the operational systems.
I know that there was a freeze on model upgrades for a while we transitioned to the new supercomputing cluster. That's done. What's on the horizon?
There are upgrades to some of the current operational systems that have to do with air quality. We have an upgrade to the GFS coming in the fall that's going to allow us to assimilate different types of observations, right? Longer term, we have upgrades to the GFS and the Global Ensemble Forecast System, the GEFS, and that's in 2023, 2024 timeframe. We're going to introduce the Rapid Refresh Forecast System. This is the new mesoscale modeling system. It's a very large domain. It covers the CONUS, the continental United States, as well as Alaska, Hawaii, and the Caribbean. Okay, so that's slated for implementation, again, a few years from now. And then even longer term, we're developing the seasonal forecast system, which will help out in lead times of up to 2 years, right? Potentially even this interannual time scale. So seasonal forecasts. And that can be a very expensive forecasting problem. So we're still trying to figure out how to use these systems efficiently for that particular problem.
So there's upgrades coming and some consolidations coming. Does that mean that certain models are going to be going away? I think I've heard that that the NAM isn't going to be upgraded any further, that's going to be eventually going away in favor of the HER, right? The high-res rapid refresh. The
NAM, the high-res rapid refresh, these are both going to be replaced by the rapid refresh forecast system. So one of the key things about this open development process is evidence-based decision-making, right? So these new systems that we're introducing that are intended to replace some pretty venerable systems like the HER, right? They need to prove their mettle. So if there is some demonstration that the RFS outperforms the RAP HER and the NAM across the board, it's an easy decision. If there's still instances where the RAP HER is outperforming the RFS, we'll have to make a considered decision on when we want to replace those legacy systems. But the future is in these FE3 based modeling systems.
In y'all's view, what is the best way for forecasters to keep up on model changes, but also to to quickly come up to speed on those biases and understand how all that would work?
So one of the concepts behind reducing the number of modeling systems is to introduce with each new modeling system a set of reforecasts. And for systems like the seasonal forecast system, we'll want to do a multi-decade reanalysis. And what this reanalysis and set of reforecast does is it establishes what those biases are. And it lets forecasters, for the objective calibration, right, and bias correction that we do numerically as part of the post-processing, that will use some of this information from the reanalysis and reforecast. But there is still that kind of intuitive, experiential bias correction that goes on in the forecaster's head. That's going to be a learning experience for them. But the idea is that with a comprehensive set of reforecasts, it will be easier for them to do that. There'll be less of the, oh my God, this is always 10 degrees off. Maybe it's only half a degree off, and that's something that they can accommodate.
For those who may not be as in tune with weather, but they hear their broadcast meteorologists speak about models, or they hear us speak about models, where does all that data come from? Could you kind of shine a light and kind of just help people understand this is where we're pulling all of this information from, and then it goes into the computer, and that's where we get the outputs from?
There are many, many sources of data. By far, the biggest quantity of data comes from the array of satellites that fly above the Earth. There are the geostationary satellites, right, where it hovers over the same spot on the Earth. And you can use that to not only look at cloud cover, but you can use those clouds to deduce wind motion, right? And then they also produce, satellites also produce sounding. So a picture of the vertical structure, a companion to these balloons that are launched across the globe twice a day that ascend and take readings as they ascend. You have low Earth orbiting satellites that also can examine things like cloudiness, ocean temperature, important inputs to those forecast systems. And then you have what we call the conventional or non-satellite systems. I already mentioned the radiosonde. You have a lot of aircraft data, right? Aircraft take off and they land, and there's some really valuable information in the profile that they see. We have surface stations at the airports and across the country that we assimilate data from. We have new observing systems coming online, things like sail drones, where one of the things that the global model upgrade in the fall is going to be able to do is going to be able to assimilate sail drone data where you can actually, these will be directed into storms and take readings there where, you don't want to send either a person or a less robust instrument, I'll say. So we can get really valuable data from this into the models by being able to incorporate this vast, different numbers of and sources of observations.
Another part of the complexity too, when you look at how all this stitches together, is the need to run a global model, and then how that translates into running a more regional scale model. So as you have as you move forward into the future, of course, weather comes, if you're running a local scale model, weather comes into the side of the domain and moves out of the domain. So what actually happens is a well-coordinated timing between global model, which then provides boundary conditions for the regional scale models at the edge of those domains. And then you have some domains that actually are movable, like with the hurricane model, and the whole domain moves up the coast. And so all these run in a coordinated manner across the system. So when you have technical difficulties, you know, we have ways in which we, you know, reinsert that information and you know, ensure that you get the most accurate information into the right domains and so on. So, you know, for us with all these local scale models, it's really important to have the quality of a global scale model that feeds all of that. So all of it in its entirety is a kind of a well-oiled system that needs to be maintained in balance. And so what always amazes me is Brian's team has to figure out all of these kind of non-linear sort of interactions of improvements. So if you make improvements to the global model, you have to ensure that those don't create negative impacts all the way down to the regional scale. And it takes quite some time to get all of that data and information to really make a well-informed information about the impact of what the improvements are that you're making.
So we have a pretty sizable contingent of meteorology students who watch or listen to this show. And, you know, obviously the meteorology is a big part of it, but I have seen a trend where more and more of them are, whether they want to or not, having to take up coding, having to take up programming. What would you suggest for these students to maybe pepper into their meteorology programs as they go through college?
I don't even know if colleges teach Fortran anymore, but the fact remains that most of our model codes, our operational model codes, are still Fortran. Now, as we're developing these new systems, although the base code might be Fortran, there is a whole set of surrounding code that you've already talked about, Java, Python. You know, these are the kinds of languages that are now seeping into not just the modeling themselves, but for a lot of the post-processing and the management of the modeling systems.
You know, for me, a lot of it was just you know, that side interest in the computing side, and you know, when I really got into the forecasting side, I figured out that, you know, that wasn't exactly for me, right? But the great part of it is kind of having some of those a bit of some other disciplines sprinkled in gives you the option to hang out in and around the weather community and really contribute to the whole weather enterprise in a different way, should you not be like the rock star forecaster that you dreamed, right? So in 6th grade, I dreamed of being a forecaster, right? You know, I got there and I'm like, well, you know, this is cool. I love weather, but how can I contribute in a different way? So I think thinking about some of those other factors, you know, may give you some additional options if things don't quite feel right when you get there. So aside from the computing aspects, you know, we're doing a lot of impact-based decision support services in the Weather Service. So having some feel about how emergency management works, or various communication skills, any sort of discipline that you can add to pepper in, I think is beneficial, because it gives you more degrees of freedom to stay and produce a fairly large impact in the weather enterprise.
Where on GitHub can we find these things, and how can we keep up with all that you're doing on social and otherwise?
So in terms of the applications, so let me see, I believe they're under something called the Unified Forecast System. That is the system of code that we use to build our operational applications out of. So go hunting around GitHub for that. The other place you can go is ufscommunity.org. All right. That is the home of the UFS, and it is where There's a ton of links with descriptions of the modeling systems that we're planning on building, locations of code, papers that have been written, and that sort of thing.
All right, guys. Well, we appreciate your time with us tonight and helping us figure out this new supercomputer deal. And hopefully you all who are listening or watching us kind of have a better understanding of just how much goes into modeling and how much science and math and technology is involved. So when you see the next model output, either from us or from your favorite local television meteorologist or National Weather Service, you kind of now know what goes into that. So Brian and David, thank you so much for joining us tonight. And thank you all for watching us here on the Carolina Weather Group. We'll see you back here real soon.